Okay, thank you, Lucy. Good evening, everyone. Thank you to Royal Society of Chemistry for inviting me to chair this event. It's a great honour to be here this evening, and it's a pleasure to come back to this chemistry centre, which is a wonderful building and is turning out to be very useful, hosting an interesting series of lectures. This evening's talk is about a very interesting topic, which is very interesting to me because I work for RWE Power and face every day the challenges of meeting the energy demand that we need to develop in the UK and elsewhere in Europe. Of course, it's an important issue too, particularly low carbon generation. And tonight's topic on energy storage is a particularly interesting one because that's going to become a very interesting area in the future as we struggle to not only fuel electric vehicles but also meet the peak of energy demand that we have with the increasing growth in wind turbines and other intermittent generation sources. So it's my pleasure this evening to introduce Professor Clare Grey. Professor Clare Grey is from Cambridge University. She started her career, started her academic life on the opposite side in Oxford, where she obtained a BA in 1987, followed by a doctorate in 1991. And following that became a junior research fellow at Balliol College. After a spell at the University of Nijmegen as a Royal Society postdoctoral fellow, she spent some time in the United States as a visiting scientist initially, sponsored by DuPont, and then joined the Stony Brook University, where she was assistant professor in 1994 and later became a full professor in 1997. She's still an associate director there, and she's part of the Northeastern Chemical Energy Storage Centre, which is part of the Energy Frontier Research Centre. I've got a whole series of awards that I won't go through in detail, but going back to the start of her career, it ranges back to DuPont Young Professor Award, National Young Investigator Award, but more recently, perhaps relevant to tonight's lecture, she was the Cavalli Lecture Medal speaker in work relating to environment and energy in 2011. Prior to that, also won a research award of the Battery Division of the Electrochemical Society and was the Royal Society of Chemistry John Jays Award winner too. Her research interests relate to solid-state NMR and diffraction methods, which she uses to investigate dynamics in materials for energy storage and conversion. She's currently Geoffrey Morehouse Gibson Professor of Materials Chemistry at the University of Cambridge, and tonight she's going to give us a lecture entitled Recharging the Planet, Prospects and Chemical Challenges of Using Batteries to Power a Low-Carbon Economy. So, Professor Clare Grey.
Well, thank you very much for the invitation to come here from the Royal Society of Chemistry, and thank you for coming to listen. And with such a long introduction, I always feel like it's quite a sort of difficult act to follow. But anyway, what I want to do today is to really focus on the challenges, particularly in terms of the chemistry and trying to use batteries in the field of energy storage for CO2 emissions. And so I don't need to remind everybody, I've worked out where the laser pointer is. Can you see this laser pointer? Okay. So the issue here is really one of dwindling resources coupled with massive increase in CO2 emissions. And one can argue about how long oil is going to last, how much coal there is around, but if we don't do anything about utilizing the increased utilization of renewables, think about ways of reducing CO2, then we're not going to make an impact on this. So what I want to do in my talk today is to go through some of these areas and illustrate how chemistry is going to play a role. So if you think about increasing the use of renewables, you have to think about where they're going to come from. And so the obvious ones are from light and solar power. So you could use some photochemistry or photovoltaic to take light into chemical energy or into electrical energy. But if you're going to go backwards and forwards, then you're going to need devices such as fuel cells that take chemical energy into electrical energy and storage in order to store the electrical energy. And this is particularly important in these so-called intermittent sources of fuel, which light and wind power are the most obvious examples. So what I want to do today is to describe how batteries will play a role in carbon dioxide emissions, tell you about what a battery is, what some of the technological requirements are to make progress in this area, where some of the fundamental scientific breakthroughs are needed, and then end up in the last half an hour to tell you something about what we're doing in this area to try and address some of these issues. So it's one of the interesting things about working in this space as a materials chemist is that there are a lot of different types of chemistries that go into the batteries that operate in these small-scale devices, such as laptops. I'm sorry, is it possible to get a better laser pointer? Because this one is dying. The small-scale batteries that are in the laptops and mobile phones. And here, lithium-ion batteries have really been a technology enabler. If you hadn't had a lithium-ion battery, you wouldn't have had a laptop that can last as long, you wouldn't have an iPhone, and you wouldn't have an effective mobile phone. And here, really the requirements are energy density, so how long you can run your battery for. But there are other requirements of safety, lifetime cost, and power density. And then you increase in size and you look at the batteries for transport applications. And here, safety is really an important game. Finally, in these very big batteries for big applications such as grid storage, then you're now interested in what are the lifetime costs and scalabilities. It's okay, I'll just do both. Still equally pathetic. Oh well, don't worry. So, if you're talking about now batteries, and I'll show you a few pictures in a few slides that are going to make impacts in this area, you're talking about batteries that are the sizes of this room. So how do you take a little cell phone battery that's this size and wire them up and scale them up that you're actually going to make a battery that has any chance of being cost effective and is going to last for the 20 to 40 years you need in this area? So just to start with batteries for grid storage, there are a variety of different uses and requirements in this space. So you can think about frequency regulation or power quality. So this is the sort of short-term fluctuations that you might get. And batteries are one of the technologies that have an ability to respond very quickly. So they're very important in this type of application. And then you have applications such as load leveling and intermittent power. So applications where you need to couple, for example, the intermittency of your wind supply or the intermittency of your solar power with the demand. And so then you need to put in bigger applications where you don't need such rapid response, but you do need to be able to have much larger storage abilities. And then you have the longer-term backup issues. So, for example, in February, there was no wind in Scotland. And so if you were going to rely totally on renewables, then you're going to have to do backup. You're going to have backup medium that's going to have to last for much longer. And so the benefits here are, as I mentioned before, that you just can't accommodate renewables without storage. So the grid is not a mechanism for storage, it's a mechanism of transferring power around. And so as you go from above 10 to 12%, depending on estimates, of renewables on the grid, then you're going to have to find a storage mechanism. Even though a lot of the technologies are expensive, if you put in costs, for example, of delaying the commissioning of power plants or the upgrades, then even the more expensive technologies such as batteries, and I'll come back to this in a minute, become viable. Plus the costs of, for example, using nighttime electricity and the fact that you just can't switch power plants off or most power plants on and off sufficiently rapidly to deal with the daily fluctuations. So again, we've got these issues that we have to deal with. But despite these issues, there are a number of demonstration projects that are now running across the world. So you're looking at sodium-sulfur batteries in an application in the US, where this is the battery here. Here's another sodium-sulfur battery in Japan, and here's the compulsory picture of Mount Fuji in the background. And just to get a sense of scale, you can see that this is a block of flats here. And so there are tremendous challenges in getting these types of batteries to work, and they're expensive and not viable unless the prices come down, unless you take into account delays in new power plants. So if we move into batteries for transportation, 24% of all UK's carbon dioxide emissions come from road transport, of which cars are by far the most major application. So what I want to do in the rest of this talk is to really think about how batteries can make an impact in this area and what we're doing to help improve batteries, particularly for this application. So I'll start by reviewing how batteries can help reduce CO2 emissions. So in the first electric vehicle is the so-called hybrid electric vehicle that you all are familiar with in the form of the Toyota Prius, which is really the prototype design here. And here, the battery in the Prius is responsible for efficiency gains via, first of all, regenerative braking. So this is when you put your foot on the brake and you convert the kinetic energy into electrical energy. And this has a tremendous requirement on the power of the battery. Because if you think about braking a car of this size, in the time it takes you typically to decelerate to coming up to a traffic light, you're having to do an extremely rapid charge. So that's a charge of approximately 3.5 minutes. And so we need to think about designing a battery that is able to handle this. So that's one form of efficiency gain. The other most important form of efficiency gain comes from the fact you can operate your internal engine in its most efficient regime. So the internal engine and the electric engine work together in terms of the torque and the load to make sure it operates in that efficient regime. And you can use a smaller internal combustion engine, which again translates into efficiencies. And so you can go from these so-called micro to full hybrids with a range of fuel savings, depending on the types of driving you do. With the micros being cars where they might only operate in a so-called stop-start mode, which is when you switch off the whole engine at a traffic light, for example. And the different batteries, different batteries are used for these different applications. And I'll come back to more about the technologies in a second. But the traditional lead-acid batteries are fine for the micro applications. But when you go to a full application, then you need a larger battery, and you're talking about metal hydride batteries. Now, if you want to increase the range when you just drive in an all-electric mode, then you start looking at the electric lithium-ion batteries and so-called plug-in hybrids. So plug-in hybrids are actually a different technology where you actually replace the internal combustion engine connection to the powertrain, and you run the powertrain via battery. And then, since your battery in, for example, the Chevy Volt, which is the prototype plug-in hybrid electric vehicle that's coming out this year in the US, is only geared to run for about 35 miles, you need a so-called range extender on board. And so in the first designs, this is going to be a combustion engine, or is a combustion engine, and the hope is down the road this might be a fuel cell. And so the idea is that you have a battery that's large enough that captures daily driving habits, and then if you want to go further afield on a business trip or on holiday, then there would be another method of electricity on board. And here you're now concerned about designing a battery that has both high energy and also power, because you still need to do the regenerative braking and all the other applications of the hybrid electric system. And so the so-called range-extended HEV here is just the old Prius, but they put a lithium-ion battery in, and now this can go slightly further than the old one, but that system is still got both an internal combustion engine coupled to the powertrain and also the battery one, so it's a slightly different system. And so then we go to the full electric vehicles, where you've got the two extremes. You've got the Tesla at 109,000. There's actually an extra zero here, which is almost right, but it's not quite as bad as that. At $109,000 going down to $32,000 in the Nissan Leaf. And what you can see, despite the fact this is a Lotus sports car and this is a small automobile, the price difference is really caused by the battery. And the battery cost is scaling directly with the range of these applications. So you've got a 53 kilowatt-hour pack here, and you've got a 24 kilowatt-hour pack here. And you've got about 200 kilograms of battery, which is costing you, depending on the estimates, about $18,000 to produce. And this battery pack takes, depending on how you do the full charge, you can do this in about 4 hours, or there's a regime where you can do this to about 80% in 30 minutes. So the hope is that, or the thought is that if you run out, you can go to a really designed petrol station, have a very long cup of coffee, and in 30 minutes you can carry on the road. And these battery packs are so-called plastic bag designs. So they're the same types of batteries that you found in your cell phone or your mobile phone batteries, but they're now about this size. And this stack design is actually a significant reduction in cost, which is helping these systems. And I'm going to come back to this type of battery design in a second, because that's the design I use in my research. And at the small scale, you've got electric bicycles. And so here's the EV Assist battery pack, where you've got a lithium-ion battery in the bicycle, which can have a significant impact on CO2 reduction. So if you think about areas where you might use this, and if you're replacing a motorcycle by electric assist, you can make a significant impact in CO2 reduction. And then places in the world, such as China, what they've done is taken these small battery packs and essentially just put a sheet of metal around them and made these very small cars that can cost less than $5,000. And they've gone into places in China where there isn't a good fuel distribution system, and they're going into consumers who've never driven before. And so that whole lifestyle with filling up with petrol and assuming that you've got the range associated with that just isn't there. And so the driving habits are very different, and so large numbers of these cars are actually being sold already. So this is just to remind you that if you were around in 1899, then the electric vehicle was actually the world record holder, and at the turn of the last century, 60% of all cars were electric. And it wasn't until the invention of the Model T Ford did the whole dynamics change, and we all shifted globally to gasoline or petrol-driven cars. And so electric vehicles have been coming back, but we have made improvements in some technologies, so there is hope for electric vehicles, and I'll describe that in more detail now. So I want to think now about what some of the major issues are in terms of putting a battery together for an electric vehicle, and where fundamental research is needed in this arena. So one of the big challenges is in capacity. So it's, in other words, how many electrons do you get out of your battery? But the second real challenge is in so-called capacity retention. So that's how long your battery lasts for. And this is just not because I presume that the audience is numerically challenged, but just to bring out how good a battery has to be. So if you think about your battery in your laptop, that maybe lasts for 2 years, and that's about 99.5% efficient, and it maybe does about 720 cycles. And then if it's about 99.5% efficient, only 3% of the capacity would be left. But if you want a battery that's going to last you 7 years, and remember that Nissan Leaf battery is costing you $18,000, then you need a battery that's 99.97% efficient at least. And even then, you've only got a capacity retention of 47%, which means you can only go half as far. So that's significant. If it's just a laptop battery, you throw it away and you get another one, and often you've gone and you bought another laptop anyhow. But that's not necessarily going to be the same for a car. So you've got tremendous challenges associated with this. You've got to think about why batteries fade, and you've got to try and understand over the timescales of 7 years. And most of us as scientists work with students who might be in the lab for 1 to 3 years, and you've got to try and capture the processes of capacity fade that might impact you down the road. And so it's a bit similar to the challenge of a medical battery that goes into a pacemaker. So if you think about it, you don't want the battery that's been installed inside a pacemaker to fail, which has significant implications. And so what happens is, in that area, you take half the batteries and you start them cycling. And then 2 years down the road, you can identify whether you've made a good batch. And then if all things are good, you put them into humans. And then you have the batteries that are running 2 years in advance. And if you see a problem down the road, then you can do a recall and get them out with 2 years' time. But you can't do this in this field because it's just much too expensive. So you've got to think about how to manage the temperature, for example, because that's one of the biggest sources of capacity fail. So just to think about the range issue. So here's the typical range from Cambridge, so it's slightly egocentrical view of life. If you drive on a Tesla, you might get up to Manchester. If you're in a Leaf, you might get to Nottingham. But then you switch on the air conditioning, or it's winter, or you sit in a traffic jam, and you're only at Leicester. And so the ranges that you're going to get are idealized ranges, assuming that you've got no heating, no air conditioning, and that you travel smoothly without problems on the M25 or other such things. So there are solutions, and one of the things that's going to happen is that you're not going to necessarily heat the whole car. So people are much happier if they're sitting on hot seats, or even in the US, if you can heat the steering wheels. It may not be quite so important for Britain. So is cost going to be an issue? So the thing about it, as I mentioned before, the battery pack scales linearly with its size. And so if you go from an HEV, hybrid electric vehicle, to an electric vehicle, you're just getting a bigger and bigger battery. And the question is, are we necessarily going to be able to afford it? So typical batteries cost about 350 to 750 kilowatt hours, $750 per kilowatt hours. And we really need to get it down by a factor of 2 or 3 to make this cost competitive, to get, for example, the electric vehicles into the marketplace. So there are other solutions, and this is the so-called better change stations. So the solution or the proposal of this Israeli company is that you wouldn't have a large electric battery in an electric vehicle, but instead you'd have these mechanized mechanisms for battery swaps. Finally, safety is the other very important aspect in this place. And so this is a Macintosh laptop that blew up, and this is a fire caused by the organic electrolyte, and I'll come back to why that happens later on. But a few of these incidents, this is a lithium-ion battery in a Prius, a few of these types of incidents will delay the sales in this area tremendously. Oh, and this is a lithium-ion batteries in the back of a UPS plane that blew up. So what is a lithium-ion battery? So I'll start by describing the old NiCad batteries to illustrate what a rechargeable battery is. So you have a negative electrode and a positive electrode, or the anode and the cathode, and you have two redox chemistry. So in the NiCad system, you've got cadmium 0 going to cadmium 2+, with releasing 2 electrons. And on the other side, you've got nickel oxyhydroxide going to nickel hydroxide with a reduction of 1 electron. And so the difference between these half cells gives you the voltage of the cells. So you need a mechanism by which the ions that are released on one side can then travel through the so-called electrolyte. So the electrolyte has to allow the ions to travel through, but not the electrons. And then at the same time, you have to then wire this up so the electrons go around and form the other part of the circuit. I normally make a joke now about the lithium-ion powered mobile phones, but anyway. So what do we need to make a battery? So we need chemistry that's reversible. And so the lead-acid battery is a very good example of reversible chemistry. So you've got lead 0 going to lead 2+ on one side, and lead 4+ going on to lead 2+ on the other side. And you've got a reasonably high voltage. This is a 2-voltage cell. But in order to increase your energy density, so how much energy you can get out per unit weight, you want a light material, and lead is not a good example of that. You need an electrolyte that doesn't react with the anode or the cathode and is stable, and so this chemistry is subject to degassing and release of hydrogen. You need electrolyte of high ionic conductivity, and you need conducting anodes and cathodes. So as you're reducing the lead 4 to lead 2 or oxidizing the lead 0 to lead 2+, you need the ability to get the electrons in and out. And of course, you need non-toxic materials. And so the lead-acid battery does well on some of these things, but not on others. So if you think about how would you get in a better, higher voltage system, if you move to a more reactive element, so a more electropositive element like lithium, you can get almost a 2-volt increase over lead chemistry and cadmium chemistry. And of course, lithium is very light. So in the 1970s, the chemist in Exxon in the US, Stan Whittingham, who was actually trained in Oxford as previously, put together the first lithium-ion battery. So he took a material, a layered material, so it consisted of layers of sulfur, titanium, and sulfur, and then lithium in between them. And then when he charged it, so when he oxidized the titanium 3+ to 4+, the lithiums came out of the layers, so it's a bit like squeezing a sponge cake and pushing out the jam out of the middle, and then he could form the layers, in this case, retain their structures, but the lithiums came out. And you could do this backwards and forwards for many, many times. And this worked because you have high ionic transport of the lithiums. In other words, the lithiums can move in the layer. You have high electronic conductivity. In other words, the electrons can get in and out of the system. But unfortunately, he coupled up the lithium-titanium-sulfur system with a lithium metal on the other side. And so instead of the lithiums going backwards and forwards nicely, when you pull the lithium out of the lithium-titanium-sulfur system, instead of plating nicely on the lithium metal, it formed these dendritic structures. And even though you put a so-called separator, typically a porous polymer membrane, these dendrites can force their way in. Once they see small little pores, they can ram their way through, just in the same way that ivy gets through concrete, short-circuit the battery, and cause the explosions that I showed you in that Macintosh laptop. And so that was pulled off in the late 1970s due to, obviously, some undesirable features. So it wasn't really till 15 years later that Sony put together the so-called rocking chair battery. And so they used the chemistry of John Goodenough, who was a chemist in the inorganic chemistry laboratory in Oxford in the 80s. So he'd been working on lithium cobalt oxide, so very similar to lithium titanium sulfide, but now you've got layers of cobalt, layers of oxygen, and layers of lithium. And they put together this rocking chair battery with now, instead of lithium on the anode side, you put graphitic carbon. And so instead of plating lithium on lithium anode, you intercalated or you inserted the lithium safely into these layers. And so the lithiums now go backwards and forwards through this organic electrolyte, which allows lithium to be transported. So I just want to stress here that it's not just a simple system where you have a cathode on one side and the anode on the other side. You make these composite structures to get your battery to work. And so your composite comprises your active material, which is, in this case, the lithium cobalt oxide. You put extra particles of carbon to create a percolating network that's conducting. So you can get the electrons in from the current collector through the carbon to the particles that you want to access. And then you hold it all together with a plastic binder so that as you pull the lithiums out and the materials flex slightly, so there's about a 2% expansion of lithium cobalt oxide as you pull the lithiums out, you can hold it all together without losing contact between the particles. So you gained this extra 2 volts from moving from lithium titanium sulfide chemistry to lithium cobalt oxide chemistry, and that becomes because of the replacement of oxygen and sulfur. And so without going into all the details, it's important to realize that the chemistries, the local environments and the elements have a tremendous difference on the voltages that these batteries operate. So here's lithium going into carbon, here's lithium in titanium sulfide, lithium in cobalt oxide, and then if you put lithium into a cobalt phosphate, you get an even higher voltage. And so as a chemist, what we can do now is to play with the different environments of the elements and of lithium in the compound and the different elements to try and tune the voltages of the materials and thus the energy density. So this is now the energy technology in 2001, comparing the energy density in either volumetric basis or in a weight basis. So depending on the application, sometimes the volumetric basis is more important than the weight basis. So here's lead acid going all the way up to lithium-ion 10 years ago, and through incremental improvements for the same chemistry, we've now increased the capacity noticeably in the last few years. So why do we need to do more research? Why do people like me spend large fractions of my time thinking about how to improve the technology? First of all, as I said, these batteries are expensive. Particularly cobalt is toxic and expensive. And the thought is that if you move to large-scale applications, even in transport, but particularly in grid storage, there's just not enough cobalt around globally to meet it. So that's a materials limitation, but you also have a capacity limitation. So again, capacity is how much can you get out of your system. And it's an interesting one in this material. So you take your layered material, and if you pull all your lithiums out, what actually happens is the layers shear, so they slip, and then you can't get the lithiums back in again. So it's no longer reversible. So what you do in practice is you leave about 50% of the ions there to allow this reversibility. So you're not actually getting the full capacity out of this material. So if you could figure out how to get all of these lithiums out, you'd have a battery that could essentially last twice as long. Then you've got a power issue. So those of you who try to charge your laptops up as you're desperate to get on a plane or on a train will, of course, know that you just can't get them out, lithiums in and out fast enough, and it's just not fast enough for an electric vehicle. And then this issue of safety that I've been talking about. So if you charge your battery too fast, instead of intercalating the lithium safely in these graphitic sheets, what you actually do is end up growing dendrites on top of the carbon, and those dendrites can short-circuit your battery and cause safety issues. And so a lot of batteries that are taken apart will actually catch light because the lithium plating that's going on even in the batteries, I'm afraid, that you've got in your own laptops. And this is the famous Dell laptop, and this is the Macintosh laptop, just to show that there's no platform dependency. So people often ask me, why are my batteries failing? And so I just thought I'd spend a couple of slides on explaining why this is a challenge. So it turns out that the electrolyte, so it's a carbonate electrolyte, isn't stable. So it's not stable below 0.8 volts, and it's not stable above 4.3 volts. And so what battery manufacturers do when they make a battery is they cycle it once, and some of the electrolyte then decomposes to form this so-called surface electrolyte phase. And so this SEI coats the graphite, forming a passivating layer, preventing further reaction. And this reaction involves decomposition of the electrolyte, but will consume some of the lithium. So you'll lose about between 1 and 2% on that first cycle of lithium. And there's a finite amount of lithium in your material. The only lithium you have is in the original amount in the electrolyte and the original amount in the lithium cobalt oxide. So any side reaction takes away lithium and results in capacity loss. And so over time, as this graphite is expanding and contracting, you can get particle cracking and increased formation of your SEI. The SEI can fall apart, the battery can overheat, and you can get increased decomposition, and the battery continues to fail. This particle expansion I was telling you about can result sometimes in losses of contacts between your particles and the carbon, so that you can get what's known as dead lithium. So these are particles within your composite that you can't actually contact electrically. And so over time, this can be another reason that batteries fail. And this is a particular problem with nanoparticles. So there's a lot of discussion in the press in particular that nanoparticles are going to save the planet in many respects. But with lithium-ion batteries, there are significant problems of introducing nanoparticles into these systems. You've got higher surface areas, more reactions, and nanoparticles move around. So they're very hard to immobilize, and so they can end up with many more problems of electrical wiring. Then there are other more serious issues. So the thing about a material, you make it in the lab, and then you pull lithium out of it. And when you've made it, when the lithium's been pulled out, it's generally metastable, which means it's not in its most stable state, and therefore over time it can decompose. So lithium cobalt oxide, if there's heat or even just time, will decompose to give the original lithium cobalt oxide and another oxide and oxygen and heat. And this heat then can cause more decomposition, and you can get this thing called thermal runaway. And it's this thermal runaway that produces the oxygen that then reacts with the organic electrolyte to cause these fires. And so that's one of the most serious safety issues. And so what is often done is to limit the practical capacity to about 4.2 volts to stay in the regime where lithium cobalt oxide is more stable. And so that's the major reason, along with the structural transformations, why you just can't get the full amount of lithium out of lithium cobalt oxide. And so this is just showing you that if you heat a partially charged lithium cobalt oxide battery at about above 200 centigrades, it will decompose and give off oxygen. So how do we move forward? We've got to think about cost and safety. We might think about non-flammable electrolytes to prevent the safety issues. And then we might come up with patches. So there's a lot of work on trying to coat materials to prevent side reactions and to add additives that increase or make the SEIs more stable. And then we work on a whole variety of different materials that are out there that might increase the capacity over the materials that are available. So there's graphite here, and there's a whole series of other materials you can consider as anodes, and there are other materials you can consider for the cathodes, and this is what I want to talk about now. So the graphite has a capacity of about 375 milliamperes per gram, so that's down here. So this is basically how many electrons you can get out. Lithium cobalt oxide is 120. So the limitation is really on the cathode. So there's been a lot of work over the years in trying to look at different chemistries. And the major emphasis has been on materials that are cheap, materials that are non-toxic. And the only elements that really are effective under those two criteria are iron and manganese. So the first thing that you might think about doing is to take your structure and start replacing the cobalt by your iron and your manganese. But the problem is that you can make a layered lithium manganese oxide, you can make a layered lithium iron oxide, but as you cycle it, it just transforms into a completely different structure, and it's a structure that doesn't like to reversibly remove lithium. You can put nickel in, but nickel is not safe. Nickel decomposes at the same temperatures as lithium cobalt oxide. So what chemists have done is mix a whole variety of different elements together to improve the performance. So a battery that's being produced by the French company Saft has cobalt and aluminium substituted to lithium nickel oxide, and that changes the decomposition temperature of the partially charged material from about 200 to 300 degrees centigrade, and so that makes it a lot safer. Or you can take the cobalt and you can replace it by nickel and manganese to make a whole variety of so-called NMC materials, so nickel, manganese, cobalt, or just nickel manganese materials. And these materials are the ones going into some of the hybrid electric vehicle applications. Then you can think about using completely different structures. So one of the problems with these layered structures is you can only get the lithiums out on one side. So they're two-dimensional structures. So you're limited by the shapes of your particles as to how you get the lithiums in and out. But if you move to an isotropic material, such as a so-called spinel, it's a material now where you've got layers of manganese and layers of going in the opposite direction, creating tunnels for the lithium. So these are tetrahedrally coordinated lithium sitting in the tunnels. And now you can get the lithiums in all directions, and you can produce very high power batteries. And so this lithium manganese oxide technology is the first system that's going to go into the Chevy Volt and the Nissan Leaf. And it's cheap because it's got manganese in it. Your manganese ions are connected in 3D, and so you get very good electronic conductivity. So that with the lithium transport and electronic transport gives you high power. The disadvantage is you've got one lithium for two manganese, so you've got inherently low capacity. So it's about the same as lithium cobalt oxide. Then there was a really interesting advance. So John Goodenough, the same person who did lithium cobalt oxide, had been looking at lithium iron phosphate. It's a totally different structure with lithiums now in one-dimensional tunnels. And in the late 90s, he'd got reasonable performance. But Michel Armand, 5 years later, he realized that if you nanosized it, so you made small particles, and you covered it with a coating of carbon, you could then find ways to get electrons in and out of this insulating material. So if you make it small, the electrons have to travel over less distance, and if you cover it with carbon, you increase the contacts with the carbon particles that you're putting into the composite structure. And so he showed you can get very good rate performance from this thing. And what he did, which is exciting for chemists, was he opened up the space of the types of materials you could look at. So instead of having a requirement that you had to have conducting materials, you could think about materials that were insulating. So you can now think about silicates and borates and sulfates and access chemistries that are much cheaper in principle. And so this material was commercialized by a company in Boston called A123 and is the system that's in the Tesla. So if you want to go and increase capacity significantly, you've got to think, sorry, I'll go backwards one slide, you've got to think about ways of just using more than one electron. So this is iron 2 going to iron 3, lithium cobalt oxide is cobalt 3 going to cobalt 4. If you're going to get significantly higher capacities, you've got to change oxidation states by a lot more. So one of the first ways of doing this was a so-called conversion chemistry, where Fuji Glass and then Jean-Marie Tarascon showed that you could take, for example, a cobalt oxide, you could react with lithium and form cobalt nanoparticles embedded with lithium oxide, and you could go backwards and forwards, cobalt 2 to cobalt 0, so double the capacity, and that could happen for many, many cycles. But with the challenge of doing it with full capacity, because you've got to move electrons and ions over quite long distances. There are other ways of doing it. You might, for example, insert lithium into a material and extrude or push out something else. So you can put lithium in this copper antimonide and extrude a copper dendrite. But again, you've got this challenge of reversibility. So if you're making a copper dendrite, you've got to then get the copper back into your material. So you've again got reversibility issues. And then you've got simple reactions, and this is what I want to come back to later in my talk, such as lithium reacting with silicon. And here you can take a silicon matrix and react with almost 4 lithiums to make a lithium silicide. But the problem with this chemistry is you've got very large volume expansions. So there are a lot of different options, and there are other ones that I haven't talked about. You can use so-called lithium-air batteries, where you can react lithium with oxygen. You can react lithium with sulfur. People are trying to move away from transition metal ions by making batteries out of organic materials. So the idea is take a biomass, instead of burning it, convert it into some useful lithium compound and use that to make battery chemistry. So these all sound very exciting, but there are tremendous challenges in all of these chemistries up here, and they're far from being commercial. So at the end of this section, I just want to say that there are significant progresses, and it's an exciting area, but we need both applied and fundamental science to make progress. So what I would argue, in addition to finding new materials, we also need to think about how these systems work so that we can scale them up for the applications that people are interested in, particularly electric vehicles. And so this is the area where I do my work in. And so when you think about this, you really need to understand, how do the materials function? How do they fail? What are the structures of these materials? And how do they change as you pull lithium out in one cycle and multiple cycles? How do the ionic and electronic conductivities change? And how can we optimize them? So I want to illustrate that now in the next 20 minutes with a few applications. I'll talk about silicon, and then if I have time, talk about these 2 other applications. So silicon is a replacement for graphite. So here's graphite with about 375 to 372 milliamperes per gram. And silicon has a tremendous increase in capacity of more than 10 times, both in terms of gravimetric capacity and volumetric capacity. And Panasonic has just announced in one of these sort of publicity things that they're going to produce this material in 2012. But yet actually no one knows how it works. And so here's the typical voltage profile. And so let me just walk people through these types of plots. So in an academic lab or in an industrial research lab, you don't typically research the whole battery. You typically make up a material with, in this case, silicon on one side and lithium metal on the other side, because you don't worry about the safety issues because you can control it. So it allows you to see what's going on. So then I then measure the voltage as I insert lithium into the material. So you have a voltage when lithium silicon reacts with lithium at about just 150 milliamperes, 150 MeV. It reacts, and then if you go to it starts with a crystalline silicon, it goes amorphous, and if you go down to close to 0 volts, then you form this metastable crystalline phase. As you charge, you can see the voltage on charge as you pull the lithiums out of the structure is quite different from that in discharge. And so this is a bad news because this gives you energy loss if you have a large hysteresis between the two. When you then discharge, you can see there are now 2 very different processes. If you go back, you actually see those processes again on charge. If you go down to low voltages, you go back now with a very different procedure than you did in this cycle. So if you go to low voltages, you get this. If you go to intermediate voltages, you get something else. So the question is, if you don't know what's going on, how do you think about optimizing a battery? Should you be cycling all the way down? Should you be cycling over limited range? So what sort of framework do you have to think about that type of chemistry? So normally, what people would do to look at these types of systems is to do X-ray diffraction. So you take a diffraction pattern of it and you see a series of peaks, and from those peaks you can say something about the structures of the material. But because your crystalline silicon converts to an amorphous phase, you don't see anything until you get to the bottom of discharge and you see these peaks corresponding to a metastable phase. So if you have no way of accessing this from diffraction, you've got to think about different techniques that are sensitive to amorphous structures. And so the first thing that you might do is to actually think about what sort of chemistries you might form. So this is a phase diagram of lithium and silicon, and these are the different compounds that you can form in the phase diagram. And if you make a battery at 400 degrees centigrade, you can actually form, first of all, this phase, and this phase, and this phase. But room temperature, you can't do this because of the kinetics of the reaction of lithium and silicon. So what we do is use a technique called nuclear magnetic resonance. So this is analogous to MRI, so magnetic resonance imaging, except that we do spectroscopy rather than getting an image. And the advantage of NMR in this field is that lithium has two NMR-active nuclei with nuclear spins, lithium-6 and lithium-7, and you can think about those as little spies or to interrogate the local structure. So it's an element-specific method. So I zoom into the lithium. It's quantitative, so I can count how many different environments I have, and it tells you something about the local environment around those nuclei. So I can use lithium NMR as a fingerprint of different local environments. So here are the NMR spectra of the different compounds. So I have a peak at about 20 ppm for this lithium silicide that contains silicon clusters. So that's a 5-membered ring. That's a star. This compound contains silicon-silicon double bonds here. And again, it's got a peak at about 18 ppm. I then get to a compound where I break apart the silicons, and I've got isolated silicon anions. I have a peak at about 10 ppm. And when the anions are isolated, it's 6 ppm. So I can relate shift to local environment. So then I can make a battery, and I can see what sort of environments I have in my real battery. So what I do is I make lots of little batteries, and I take them apart, and I run spectra on each of these batteries. And so the first two batteries are actually the reaction of lithium with a carbon in the material that I've added. And then the next ones are all lithium reacting with silicon. And so what's quite interesting is as soon as you react with silicon, you see the peak that comes from the clusters, and you see the peak that comes from the isolated silicon. And this is not the same route that the battery took. It's not the thermodynamic route. So if you had a thermodynamic route, you would expect first of all the clusters to form, and then you'd form isolated ions. But instead, because lithium is so difficult to break silicon bonds, you go straight and you aggressively rip apart the silicon, and you form both clusters and isolated ions. And at the end of the reaction here, you then break the clusters apart, and you form isolated silicon ions. So then you can think about other ways of looking at local structure, and one of them is to take the diffraction pattern and Fourier transform it. And when you do that, you get a so-called pair distribution function analysis. So this is a diffraction pattern of the amorphous structure that most people are familiar with, glass. So if you take the diffraction pattern of glass, you get peaks that correlate to the different distances in the solid. So the first peak is the shortest distance, so the silicon-oxygen peaks, then comes the oxygen-oxygens, and then come the silicon-silicons. And the intensity of these peaks tells you how many of these environments you have in the solid. So you can go from your crystalline silicon structure with the silicon-silicon peaks in the first coordination shell, the silicon-silicons of the tetrahedra, and the silicon-silicon peaks across the tetrahedra. You can cycle it to deep discharge and then up again on charge, and you can see it's converted to an amorphous structure with no long-range structure, but you still have two peaks here that come from the tetrahedra in the material. So you can see that the amorphous structure is still built up of these silicon tetrahedra. And then you can look at the NMR on charge of this material, and you can see that it goes back without forming any clusters on charging. So by using these techniques, you can build up a model for how this system works. And then you can go on to do exactly the same thing in the subsequent cycles. And so with this information, you can then figure out what are the optimum regimes to cycle this system. So with that as a sort of fundamental basis, I will then have to then think about what happens when you're really cycling in real time. And so in order to do that, I developed an approach taking so-called plastic batteries. So I started off with the big batteries that go into the Nissan Leaf, but you can downsize them to about 1 centimeter, and you can actually put them in your NMR spectrometer, you can wire them up, and you can watch as you're cycling the batteries and see what's going on in real time. And so this is a plot of the lithiums, assuming it works. Come on. Here's the electrochemistry going on, and you can see the formation of the clusters as you're lithiating the material. And then you can see the isolated ions, but you can also see this negative peak that comes and disappears. So if you didn't see that, it's easier to see on a contour plot. So here's the reaction of the carbon, here's the formation of the clusters, here's the formation of the isolated ions, but you're also seeing this very de-shielded lithium environment. So the question you then have is it just we can't make good batteries? Are we just missing something? And so the mystery was actually solved when my student left a battery he'd discharged, and he went away for 600 minutes, had a long coffee break. When he came back, the chemistry had completely changed. And so what's going on is a so-called self-discharge process. Your lithium silicides are so reactive, they react with the electrolyte, and they themselves are oxidized. So you've lost that negative peak. And so it's not that we would have different chemistry in our batteries that we look at by in situ methods from ex situ methods, is that the reactions are just too fast to capture. And so once we recognized that, we went back and we looked at our experiments in ex situ and did things much quicker, and we saw the chemistry was the same. So then the question is, how do you solve it? And it turns out you can take a binder, such as a cellulose material, and that cellulose material covers the silicon, and you can reduce this decomposition reaction so that instead of happening in minutes, it now takes about a month for it to happen. And it's solving these types of discharge mechanisms that's important if a material is ever going to be commercial. Unfortunately, it's not perfect, because as you add lithium into the structures expand by a tremendous amount, the particles crack, and you expose fresh surface for these reactions. And so the challenge now is for us to try and identify ways of healing the cracks and passivating that surface so that we can slow down these processes so that they take even longer time periods than months. So just in the last few minutes, to think about other information we can get from these in situ studies. So I focused on the silicon, but if you look at the lithium is a metal and it has a peak at about 250 ppm. And when you discharge your battery, the lithiums go from the lithium to the silicon, so this is the discharge. And if you look at the intensity of the signal, it really didn't change very much. But on charge, you pull the lithiums out of the silicon, they go back, and now the intensity increases. And so it looks like you're making lithium for free in your battery, which is probably what went on in the 17th century in this building, but these days we don't do that much alchemy. What's going on actually is I'm forming a dendrite. So it's these dendrites I talked about in the beginning of my talk. So as I go back here and I return the lithium onto the lithium anode, it's forming these dendritic structures. It turns out that I can't get the radio frequency pulses that I use to do NMR through a block of lithium. I can only get through the first about 15 microns. So I have a way of seeing these dendrites and separating them from the lithium metal. And just to remind you, it's these dendritic structures that can be serious safety issues. So what I can do now is devise a way for testing electrolytes to see which ones are good for dendrite formation and other. And so this is one where I've just replaced the electrolyte by a so-called ionic liquid, and I'm cycling backwards and forwards with constant lithium. So here's the experiment, backwards and forwards, and you can see it fails here, where you form a dendrite, and you can use the NMR to track and see the formation of the dendrite before it actually appears in the electrochemistry. So this is a movie that sometimes works. this is an experiment where we're now seeing what sort of current do you need to produce dendrites. So I'm going backwards and forwards, and here's the lithium signal, and you can see when the current goes up, you can now start to see the formation of the dendrite come up here. Again, before you see any signature of decomposition from the electrochemistry. So then, the next thing we wanted to do to really help understand this process was to work out where the dendrites were occurring. And so in order to do that, what we're doing now is MRI, just to return back to the original technology. And so here's the formation of the lithium dendrite as I cycle the battery backwards and forwards. So just to end, I just want to give you one nugget of how this chemistry or these NMR techniques can be used to actually make new materials and improve them. I want to end by talking about these layered lithium cobalt oxide structures that I mentioned in the beginning. So you can take the cobalt and you can replace by manganese and nickel and make a whole variety of different complex structures. And I just want to focus on one very simple one where I've taken the cobalt and I put in 50% nickel and 50% manganese. And when I charge this at a slow rate, so C over 20 means I take 20 hours, it gives you a capacity of about 200 milliamperes per gram. But if I charge fast at 4C, which corresponds to pulling the charge out in 1 hour divided by 4, so 15 minutes, you can see the capacity decreases significantly. So the question is why? So what we did was to examine the local structure of this material. So here again is the NMR spectrum of the material. And by looking at model compounds, so compounds where I know the structure, I can assign this peak to lithium in the layers. And this peak, it turns out, happens to be from the lithiums that are moved from this layer to this layer. So they've swapped. So lithium and nickel are about the same size, so they can actually, when you make the material, swap and form defects of nickel sitting in the lithium layers. And so this nickel stops the lithiums moving rapidly through the layers. And so once we'd realized that, we then thought about how to make an improved material. So you can make the material with sodium, you can replace the sodium by lithium, and when you do that, you can see you get a tremendous increase in the performance of the material, and you have a material that you might be able to use for a hybrid electric vehicle. So with that, I hope I've shown you that we're able to interrogate or look at the local structure with new probes of local structure, and this information feeds directly into the design of improved materials. Prospects. Electrification is the most according to me at least, the most practical way of short-term CO2 reduction. You've got to think about where the electricity comes from. HEVs are reality. EVs, predictions vary dramatically, and we can discuss the way forward in questions later on. And I want to just end by thanking the one student, Barish Key, and postdoc Rangeet Bhattacharya, who are very much involved in the chemistry I described today. So thank you very much for your attention.
Thank you very much, Professor Grey, for giving us a very clear explanation of the problems that you face, not only in understanding the materials and how the materials are causing difficulties in developing new materials and failure mechanisms, but also how you're using your techniques to develop and understand them. We do have time for some questions. I'd like to remind everyone that this event is being broadcast live on the web. And so we have two assistants who are coming around the audience with microphones. So if you could just wait until the microphone gets to you before you ask your question. So does anyone have any questions for Professor Grey? Okay, gentleman halfway down the first row. And then, yeah.
Thank you. You mentioned in your talk that there's a shortage or there's a material limitation for cobalt. Is there any limitations for lithium?
I don't think there are. I know that that's often raised, but if you look at the analyses of most, albeit lithium companies, they have enough to produce lithium in battery, in vehicle applications, and they've done analysis depending on whether you have sort of slow penetration versus wide-scale penetration, and what the rate of penetration of EVs in the marketplace will decrease or increase the time before you're going to have to recycle. I mean, I personally think that you're going to have to recycle because of the cobalt or whatever technology, and so you'll get the lithium out that way. So some scenarios have you recycling in 35 years. Some scenarios have you recycling in 235 years. And you don't even need to go to Afghanistan or Bolivia to get your lithium in those scenarios. Those are based in lithium in safe countries. I think the lithium is not the issue. I think that there are many other issues, not lithium is kind of a sort of side issue.
Okay. Gentleman on the front.
Hello, I was speaking to a car manufacturer and they were saying to me that lithium titanium batteries are the best for fast charging. Is that true, and can you explain why?
So when they say lithium titanium, do you say titanium oxide?
I don't know, sorry.
So that's referring to the anode. So you can replace carbon by a lithium titanate, and you up the voltage from close to sort of just above 0 for carbon to about 1.5 for lithium titanate, and that is a very fast material, but it's considered a safe material because you don't obviously plate lithium because your voltage is that much higher on the anode side, and so you can push it faster. It has limitations because it's got a much smaller voltage. So there are some companies that are pushing it, but it's also got side effects. It's not as stable as people used to think. Most companies are not putting the titanate in there, but it is one of the materials being considered. But because you're going from almost 0 to 1.5 volts, you're reducing your battery from about 3.5 volts almost down to 2 volts. So the pros and cons.
So it was just them lying, really, because they said they could recharge it in about a quarter of an hour and it would last for 24 years. So that's just...
Well, that's good.
That's just rubbish then, really.
No, I mean, it is a material that's being considered, but it does have its disadvantages as well. So certainly there are companies that are putting lithium iron phosphate together with lithium titanate to make the ultimate safe battery. And it is a fast-charging battery. But remember, when you charge fast, you've got to have... It's not just the anode, it's also the cathode. Because if you charge too fast and you get overcharging on the cathode side, then you're back in safety issues. But lithium iron phosphate is a fast material. Lithium manganate is a fast-charge material. Unfortunately, lithium manganate has issues of dissolution, so I doubt that 20 years number based on the cathode. The titanate may survive, but the cathode is going to be your problem. So it's certainly a material that's being considered.
Okay, I think I saw a hand go up on this side as well. Gentleman halfway down, or anyone else who wants to? Right at the very back there.
One of the problems we have in this country at the moment is the lack of young people going into the sciences. How visible could you make this chemistry so it could be demonstrated to the extent of what's going on? Would it be possible to any extent?
Well, I did something on the program on the BBC the other day on wonder stuff. And we had a very nice demonstration, which I should have really shown here. Carbon, when you insert lithium into it, changes from black to red to gold, or sort of the other, yellow, red, black. And so you can see visually how lithium goes in and out of these structures. I mean, I personally think, although you may not have agreed with my lecture, that this chemistry is actually a very good illustration of science in action. And it's very easy to make the connection of the lemon battery that people or that children have played with, and all just tinkering around with batteries through to why it's really important. And also just in a sort of starting science level, there's a lot of inorganic chemistry for first-year undergraduates that's quite obscure. I mean, the Nernst equation is the sort of most boring thing that people do. And things like ions changing coordination environments that are actually made quite interesting by these types of applications. So I think and I mean, I do try to do a fair amount of lectures, and there are people, I mean, I think trying to make kits would be quite useful as well. I spent, I was in the last 18 years in the US, and I used to do a program for high school kids on Long Island where we'd make batteries. But it's quite difficult to do sort of the high temperature chemistry, and the assembling of a battery has to be done in a glove box. So at least, or in dry conditions. So some of it's difficult to do, but some of the chemistry is transferable into school chemistries. And then you end up with, so we made lithium manganese oxide because it's not toxic. You can't do lithium cobalt oxide. And how do you, when you make these materials, how do you characterize them in a school environment where they don't have a diffractometer? So you can. There are ways to do it. I mean, I made chemistry that was so straightforward that it couldn't fail, so therefore it worked.
Absolutely fascinating. Thank you very much.
Thank you.
Okay, do we have any more questions? Gentleman in the middle on this side.
A slight diversion, Professor.
Yeah.
Do you see a future for fuel cells? They were sort of 20 years ago. They were going to be the future, but they seem to have.
Well, I mean, I think that it's very important in terms of science research not to shut down options. So this country and in the US had a very large fuel cell program, and now the politics is such that fuel cell research and the hydrogen economy is no longer the thing. And I think that's not a way to go about it. I think there are some challenges in fuel cells, but solid oxide fuel cells are largely, I won't say they're solved, but they're practical, they're just expensive. I think that I would see a fuel cell being in a car as a backup in 15 years, yes. There are challenges, but the serious challenge on the fuel cell being the platinum and the cost of that, and just the cost of the membrane. But I don't see why we should give up on them. I mean, I think it's just not it's not a sensible strategy when the battery has challenges as well. And in terms of storage, it's much more effective to store energy in the form of a chemical fuel than in a battery. And so I think we have to find ways to improve fuel cells, because the energy density of a liquid fuel is just so much higher than a battery. So that's my answer. I don't know if it answers it, but I think it's a challenge that we have to address and shouldn't give up on.
Perhaps time for one or two more questions, if there are any more. Okay.
There's one in the
Right
back.
at the very back then.
How do you see the temperature sensitivity of batteries playing out in vehicle applications? Do you think there'll be certain areas where you might have to have a different formulation, or certain areas that will be no-go for batteries?
So, I mean, first of all, the temperature of control of batteries is the most key thing to longevity, and so active control at 40 degrees centigrade is absolutely critical. So your question is, do you think...
To 40 degrees centigrade, then some parts of the world you'll find it very hard to reject the heat, and other parts of the world, if you've left it for a while, it'll be at minus 40. And I mean, there's sort of temperate regions where all this is doable, and then there's extreme regions where we're used to having vehicles now where batteries you'd have different challenges anyway.
I mean, yeah, and I think what you're saying is a very important point, but I think that we're so far away from market penetrations. We should do the areas and the parts of the world where it's easier. Cold is easier. I mean, Canada has systems where you plug your cars in anyhow to keep them at reasonable temperatures. Saudi Arabia and hotter parts of the world are much more difficult, and things go wrong much more quickly. But then there are higher temperature systems. Actually, one of the strategies for safety is to get rid of the liquid electrolyte, go for a polymer electrolyte and start operating at 100 degrees, 120. I mean, it brings with it a whole series of other challenges because you've got corrosion issues, cracking, and so there's no question that that's an easy solution, but there are other options to explore. But one of the frustrations I had a number of years ago was that the Department of Energy, that's been very responsible for sort of setting goals, has this tremendous temperature range that they want to sort of live under. And I think you can't often have materials that will do everything. And so yes, you may have to have batteries for the winter and batteries for the summer. And okay, but we sometimes put tires on, so that's not an impossible thing. But until we get higher market penetrations in places like Britain that rarely get above 25 degrees centigrade, this summer anyhow.
Okay, then one last question.
How might flywheel energy storage systems compare with battery systems?
Would you mind just repeating that with the microphone, please?
How would flywheel energy storage systems compare to these battery systems?
So the question is, how would flywheels compare? I mean, they're different applications. I mean, there is some discussion of flywheels in cars, but the energy density in storage is not as great. They are being considered for static applications, for sure. I don't believe the energy density is as high, although they're much more scalable. There are still safety issues with flywheels if you have things that go out of control. I'm not much of an expert on the other challenges, but I do know that energy, the amount you can store in them is less. The rate at which they respond is reasonably fast, but actually batteries can be faster than a flywheel.
They wouldn't deteriorate with time and usage.
I mean, that's absolutely right, that they will have longer times, for sure. Yeah.
Perhaps I can just ask your opinion on one thing that I think is probably everyone's very, very interested in. You've seen these battery technologies develop over a number of years. So how long do you think it will be? You probably know where I'm going with this. How long do you think it will be before we've got one of these $30,000 vehicles that's about the price people are used to paying for a vehicle that will give us a sort of 500-mile range that we're used to getting from our tank full of diesel?
Well, I think you know the answer to that question. So you'll notice my prospects. I mean, I think that plug-ins are really realistic. And there are a lot of other factors in place that are going to make them realistic, like the CO2 legislation in Europe. I mean, so for those of you not aware of the issues, that because of the need to get CO2 down in fleets, a lot of the car manufacturers are going to have to sell electric vehicles or plug-ins so they can continue to sell SUVs or large BMWs. And so there will be increased electric vehicles, for sure. But I'm not myself personally convinced that actually an electric vehicle that's going to go 500 miles might make sense for most people. I mean, my problem is I live in Cambridge. I don't have a car. I bicycle. I mean, I have a car in the US, but that's another story. But I would want a car that could go 300 miles when I go a long distance, and there isn't a car available. And you don't want to be carrying around the weight of your battery so that when you want to do 300 miles, it's there.
Exactly.
So we're a ways off from a car that's going to go 300, 400 miles, unfortunately. I'd like to be able to say that's not the case, but a cheap car, we are a ways off. There are technologies, but they're not.
We're not there yet.
They're not there, and there's no clear roadmap for them. I mean, it would be just like saying the fuel cell is going to be ready, and yet we're still in the same position. So I could sit here and I want to say there's a trajectory, but right now I don't see that trajectory. There are technologies, but the trajectory of getting them to work cheaply is not there yet.
Okay. Well, I'd like to thank you very much for a very interesting, clear and informative lecture this evening, and I hope everyone else will join with me in saying thank you very much for coming along and telling us all about this topic. Okay.